action. Hello and welcome back to Calculus 1. We are starting chapter 4 and we are going to start chapter 4 at section on minima and maxima. We're going to talk about the concept of minimum and maximum and a function. Why? Well, we are interested in it. We would like to know maximum profit, minimum cost, minimum amount of energy to accomplish something. What's the minimum amount of power for a machine or something like that? So we are constantly optimizing. And then we can do that through equations. We can do that through graphs. Before we go and do any particulars and calculations, we have some words and concepts that we need to understand before we start doing the math and calculations. So let's start with the wording of absolute versus local mean and absolute versus local max. We also have absolute to be global and local to be relative. So we have two sets of words that mean the same thing. So depending which book you read, you will get all of those. So we have absolute, also known as global, mirror max, or you have relative, also known, so global mirror max, or we have relative, also known as local mirror max. So these are the words, and now we need to understand what these words mean. So let's first take a look at function f of x. That will forever go in here. I am not placing this in the xy coordinate system because that's now irrelevant. We are looking at the peaks. Now what is happening here? At these top points, we can draw horizontal tangent line with a slope equaling to 0. Also, we get the same thing at this minimum situation here. So, anytime when you have a horizontal tangency, which is the horizontal tangent line with slope equals 0, hence horizontal, we have a min, we have a max, or a max. Now we need to also distinguish between absolute and relative, or global or local. If you look at the peak to the right, the maximum value on the right, that one is going to be labeled as absolute max. And the reason is why it's absolute because highest point in the entire domain. So there are no points anywhere on the entire function that are higher than this point. So this is the highest point. This is the Mount Everest of the entire graph, forever. So we call that absolute maximum. But now, if you look at the left one, that's maximum as well. But it's maximum in its own little neighborhood. There's a bigger boss, all right? So now, the one on the left will be called relative max, also known as local max. Why would we call local? Because it's a maximum in its little local community, right? And now we go for this minimum over here. What do you think the minimum is? Absolute or relative? Relative, very good. It was a 50-50 chance on that one. Now, why is it relative? It's relative because if I extend this tangent line, all of these values going forever are lower than our minimum. Now, we said that absolute min, absolute max happen when those points are the lowest or the highest within the entire function. So just because, right, below this line, just because below this line there are infinitely many points, or any points, that are lower in y value than the one at the relative min, the minimum has to be relative. So it's only the minimum in its own neighborhood. So now I can draw a function f of x equals square root of x. And since the right-hand side is always going to climb up, we are not going to have any max or a min on that side. However, on the left-hand side, over here, I have absolute minimum. And it's absolute minimum because that is the lowest possible point on a graph. This graph will continue up and up and up and up forever without ever bending back down to x-axis. So 0, 0 in this case is the absolute minimum, and there is no max at all. So we have some functions that have min or a max or both, and some functions do not. So infinite linear line that stretches forever in those two directions, it does not have min or a max. So hopefully we understand. Now let's take a look at okay, can you populate this picture in your notes? So call this g of x. You need to label each of mins and maxes that you see over there as relative or absolute. All right, so we have these three, which would have the horizontal tangency. So what do we have here? The first one over here. Which one? Okay, but which one? Absolute min. This is absolutely lowest point, lowest y value of all xy, right, that we have. There is no lower point than this. What's the lowest point on our planet? Come on, they buried the Decepticons there. There we go. Very good. I'm learning history. How about the other minimum? Relative minimum. How about the max over there? Why relative? Exactly, because if I pick this point over here, it's taller, it's higher than my max. So in order for something to be absolute max, all other points on graph have to be below. So in order for something to be absolute min, all other points have to be above it, right? You are looking for absolute min, absolute max. Great. All right, now, red. Min max occurs at critical point. And now we have to define a critical point. Definition. An interior point C of the domain of F at which f of c prime equals 0 or f prime of c fails to exist is called a critical point. So an interior point C of the domain of F at which C prime of F prime of C is equal to 0 or F prime of C does not exist, it's called a critical point. We can find these points using calculation, and this definition is going to help us in that. We can see that we can force the derivative to be equal to 0 and compute the values at which we have critical points. Or if we are able to recognize that the derivative doesn't exist at that point, it's also a critical point. So let's take a look at some examples. Y equals x squared is a parabola. You already know the answer. I'm looking obviously for min, max, whatever I can get. So you already know the answer. You know which one we have. You know the classification, right? And you even know the location at which it happens. So can you give me all of that? What is it? What kind of extrema do we have? Min or a max? Min. It's min. Now, tell me more about that min. What type? Absolute min. Very good. And where? 0, 0. At 0, 0. So you already know 100% of things that you have to compute for more complicated functions later. Now let's compute. If I have that f of x is equal to x squared, f prime of x is 2x. And now I am going to set that equal to 0. So this is what I do. I set f prime of x equal to 0 because I want to force the values where derivative is 0, because that's where the tangent line is horizontal. Because f prime of x is f prime of c is equal to m, and we need horizontal tangency, right? So that's our reasoning. Why? We know that min and max occur every time when we have horizontal tangency. So if I set derivative equal to 0, I am forcing derivative to be 0, which is m equals 0, and horizontal lines are the lines that have m equals 0. So that's that part. And now, wow, we have an equation to solve, right? So whatever, we can have exponential equation, logarithmic equation, trigonometric equation, because our function f of x could be anything, right? So now you have to know how to solve all types of equations from your algebra and pre-calculus, obviously. Now we're solving just 2x equals 0, so that's easy. Divide both sides by 2, x equals 0. So now we have the x coordinate of our critical point. That's known as the critical number because it's just x value. So this is critical number. And then we're going to plug that critical number in original equation to come up with the y value. So that's z0 squared, which is 0, from where we have 0 for x, 0 for y, and this over here is critical point. Now we're happy that this graph was easy. We already know what it looks like. It's x squared. So there we go. Problem solved. Now, since this graph was easy and you know it, you memorized it, it's easy for us to make the min-max type of claims, right? We know it's a minimum, we know it's absolute minimum, and we knew where it happens even without calculating. But the method shows you that we are able to compute this. So let's take a look at a different function to come up with this. Ooh, shiny. I will leave the So locating critical points, problems 23 through 36. Let's pick 28 to start off. It's a polynomial. So 28 gives you a function f of x is equal to 4x to the 5 over 5 minus 3x cubed plus 5 on negative 2 to 2. So we know the drill. Take the first derivative of x. In our case, drop 5, so it's going to be 4x to the 4th minus x squared, and the derivative of plus 5 is 0. So now we have this, and again, we are going to set this equal to 0 to find location for critical points. Factor out x squared. We have 4x squared minus 1 equals 0. Use the zero product rule to separate these, so x squared equals 0 and 4x squared minus 1 equals 0. When you solve the first one, you get x equals 0. When you solve the second one, well, this is the difference of squares. And if it's a difference of squares, it's going to be 2x minus 1, 2x plus 1 equal to 0. And now you can use the whole thing again when you set each parenthesis equal to 0, and you will get 2x minus 1 equals 0, which gives you x positive 1/2, and 2x plus 1 equal to 0, which is x equals negative 1/2. And we have 3 critical numbers. You can take these values to the original equation and compute their y values to get critical points. And yeah, we have to do that. So I shouldn't be boxing these because these are critical numbers. So I'll box them maybe gray. There you go. So now those are critical numbers. Now we're going to find f of 0. And f of 0 is 0 because it's 4 times 0 to the 5th over 5. Oh no, I lied. Minus 3 times 0 cubed plus 5. So the whole thing of f of 0 is 0. No, it's 5, sorry. It's 5, which creates a point 0, 5. That's a critical point. Then now we're computing f at 1/2. We need to compute the y values. So compute at the half, and what do we get? We get 4 times 1/2 to the 5th divided by 5 minus 3 1/2 cubed plus 5. So we just compute this. So 2 to the 5 is very good, 32. Cancels with 4. So it's 1 over 8. So 1 over 8 over 5 minus 3 over 8 and then plus 5. So let's compute this. This is 5/8 minus 3/8 plus 5. This becomes 2/8, so 1/4, so 5 and 1/4. So that gives me the formula which says 1/2, 5 and 1/4. So that's the point. We have the point because we were able to use the procedure to figure out the x's we need, and then we're using function to calculate the y. The only thing that is left is to do the same for negative 1/2. Now these exponents are odd, so that will just kick the minus signs in front. So we have negative 4 1/2 to the 5 over 5. And then the negative will kick out here, so that's plus 3 over 8, I guess. And then minus 5 at the end. So this is okay. So let's take a look now. Well, it's the same numbers. It's negative 5/8 plus 3/8 plus 5. So we have negative 2 over 8. So that's like a quarter. Plus 5. And the answer is 5. Sorry. Negative 1/2. And the same as this guy, so 1. There we go. Done. Can anyone tell me what I did in this problem from scratch to finish? What have I done? What did we go through? What is this all this stuff? Critical point. Right? Critical point. What I have done in this example is I took the function 4x to the 5 over 5, right? So I took that function and I found its derivative, and now that I have its derivative, I set the derivative equal to 0 and go through whatever algebra I have to. Right. So any algebra that I have to come up with critical numbers. Once I have critical numbers, I place each one of those critical numbers one at a time back in original formula to calculate y values. Then I have x comma y, and those are points that we can use on the graph to do the, right? Because you have, I mean most of the time, not always, you have min and max at the critical point. There is one more concept called inflection point that is trying to confuse all of these things. We'll get to it today. But it exists. Yes?
Wouldn't it be minus 5?
Oh yeah, minus 5 over here, you're right. So if that's a minus 5, that's a, yeah. So negative 5. Good. All right, what else? Let's take a look at some more interesting questions.
Can I ask a quick question? Let's go to the top a little bit.
The top a little bit.
Derivative. No, not that much. Just the beginning of the 28.
Oh.
Sorry. Let's go up tiny one. So 4x to the 5th over 5. Right? So I thought
5x to the 4, and then 5 would cancel.
I thought that you have the parameter to the independent variable is 4, and it's a constant, so you can kick that out, and then you can just work with the x to the 5th over 5, and that's equal to x to the 5th times 5 to the negative 1. So I did it that way. That would give a different answer.
Why 5 to negative 1?
To get it out of the denominator.
But that's a constant. We don't do
And then
anything
you
with
just
it.
scratch it off. Right. But so then I ended up with 16x to the 4th because I took the 4 out at the beginning.
But it doesn't matter if you kick the 4 out in the beginning. If you kick the 4 out, and you still have to take the derivative
Of x to the 5th.
over 5, yeah.
So then you have
So you
4x
4 times, and now you copy 1/5 because that's a constant, and the derivative of x to the 5 is 5x to the 4th. These guys cancel, and here's your 4x to the 4th, which is this. Right? So you copy the 4, and you take the derivative of the inside, the derivative of, right? Cool? All right. Problem 33, trying to hit up as many functions as I can. So f of x is equal to 1 over x plus ln x. And they want the solutions on, oh, they didn't specify anything. Good. Oh, for a moment I thought. That's extension. So we'll have to check at the endpoints for the closing from the endpoint. Come on, I waited a month. LNX. That's clearly LNX. LNX, right? Is it better LNX? Foreigners. All right, let's go. Three exams in total, unless you say so find derivatives.
What's his name? Ashley. We all have a you said really good.
I don't have that much material. Probably say that.
Saying how you would ask him any questions.
When you are learning, it's one of the integral things. You don't want to know how, you want to know why. Now let's see who drives this here. Who's the challenge? Yes. On all of them. Very good. No, we'll come out for work. Or is it Alright, so people on that. I don't have my credit card still on file, and I forgot about it.
My grades haven't What?
I like you.
Yeah, but you go.
This all this stuff. Well, I think right now, yeah. They put over time, I want to use an so, but I need more than one. Generally, yeah. I'm going to try to do it. No, you don't get it. But I want to get well, I guess you guys are done, so I'm just going to plow through this now. Let's take a look at the problem together since you all have the solution already. The derivative. F prime of x is equal to negative 1 over x squared plus 1 over x. And we set that equal to 0. The way we solve this is we take the negative 1, put it on the other side. So what I have is that 1 over x is equal to 1 over x squared. Cross multiply to get x squared equals x. Then subtract x and get, when you factor x, get x equals 0 and x equals 1. Now, can we have a critical point at x equals 0? And the answer is no. Very good. Why can't we have one? What do we have at x equals 0? So what do we have at x equals 0? Looking at this function. Look at the function. What do we have at x equals 0? Yeah, undefined. We have the vertical asymptote. 1 over x has the vertical asymptote at x equals 0. ln x has a vertical asymptote at 1 over 0. So there is a vertical asymptote there. So this is not a critical point. This is a vertical asymptote. So we don't use it. So because VA, vertical asymptote. Now, so the only one that we have is x equals to 1. We plug that in to find the y value. So f of 1 is 1 over 1 plus ln of 1. How much is ln of 1? 0. And then we get 1. So 1, 1. That's the critical point. I have no clue whether this is a min or a max or maybe that inflection. I don't know. We could calculate extra points around and see whether it's, going into a smiley or a frown. But we'll get some good things going soon, so we'll see. Now let's take a look at this situation. F of x equal absolute value of x. What is the derivative of this thing? Let me see the honors calculus over here. Yes.
For one part.
You have to say the domain is 0.
Yeah, domain is from negative to infinity.
Oh, it's from negative. Oh, the range is
Yes, range. So, the derivative is what?
1.
And -1. So the definition for absolute value of x is x for all x is bigger than 0 and negative x for all x is smaller than 0. You can put equal anywhere. So the derivative would be the derivative of x is 1 for all x is bigger than 0 and the derivative is -1 for all x is smaller than 0. You see that at 0 the derivative wants to be two values at the same time. So absolute value of x is not differentiable at x equals 0. You know what that means? You see this f prime cc fails to exist? It's a critical point because it doesn't exist. And the derivative at that point doesn't exist. So, fx is not differentiable. And we know it's not a vertical asymptote. So, and we know it is not a vertical asymptote. So the only thing it can be is the critical point at 0, 0. Now we also know that from the graph. This is not something that you are now doing to verify what you know from before. This is just you practicing basic skills so we can do some diabolical problems later. So me going through x squared and stuff like that, no one cares, right? Because the goal is to analyze ln of sine x squared. Yeah, right? So now if you look at the graph of absolute value of x, do we see a minimum at 0, 0? Yeah, right? So critical point at 0, 0. See, how do you know that you have a vertical asymptote? You compute your first derivative equal to 0. You also find all of the points where you can differentiate, and you have a list of critical numbers. Then you take those critical numbers one by one, and you plug them in original equation. If that calculation gives you back does not exist, you hit the vertical asymptote. But if it does give you a y value back, well, you have a critical point. And that critical point is min, max, or inflection, depending on situation. Now we'll talk more about the inflection point in next section. So now we're just dealing with these calculations. Now the next part is what happened. I already had a question about this. We never used it, right? So what's up with that? Well, let's talk about it. When you are on infinite domain for polynomials, polynomials are going to do something nice and cute in the middle and then go to a negative, go to positive infinity, and they will not change the behavior once they kind of start going towards infinity. Where trig bends, right, and does the wave. So what happens is that like what happens on the closed domain? Let's put it as a hold on. There we go. What is happening on the closed domain. So what is happening at a closed domain? Well, let's just take a look. I already mentioned this before. If I have a linear line that goes on forever, this linear line has no min-max. So no minimum, no maximum on this line, because it goes up in such a way it will never stop, so you are never able to claim this point is a max or this point is a max, because it goes on forever. And the same thing goes for the bottom part of this line. Now what I'm going to do is I'm going to take this same line and I am going to put it on the closed domain. That means I'm going to chop off parts of this line. And I am actually throwing away the parts that are going. So instead of having a line like this, I'm going to pick like that and just keep this much between A and B. So this is on the closed domain A, B. This is on the infinite domain negative infinity to positive infinity. Do you see that you created absolute min and absolute max as soon as you restricted the domain? You all see that? So the line on top has no min and max because the line will continuously grow and continuously fall to the left. So no absolute min, no absolute max, no any kind of min and max in this case. But the one on the bottom has absolute min and absolute max on the endpoints. So this one over here becomes the absolute max, and the location is B, f of B. And the one over here becomes the absolute min, which is A, f of A. And this is the interval AB. Closed interval AB. So now what we learned from here is that on the closed domain, AB, f of x will have ABS min / max. Both of them. So let me give you another example. Be very careful the way you draw this, because I'm going to have horizontal tangency here, horizontal tangency here, and now I want to name all of these points. So what's the one on the all the way on the bottom over here? What is this? Come on, guys, what is this? Thank you. This is why I'm depressed. I'm talking to 30 people and no one is like, So we have absolute min. How about the other one over here? Relative max. Now, how about this point? The f of b. This one over here. Absolute max. And how about this one? Relative mean. So what do we learn from this graph? When you are on the restricted domain, when you are on the closed interval a to b, your absolute max and absolute min have to be somewhere. Now, they can be either on the endpoint or on one of the things inside, right? One of the critical points. So now what we are going to do, the next example is we are going to do the previous example 100% same way, and that procedure gives us only the situation for the inside. Then we are going to have obviously y values for those, and then we are going to compute y values for the endpoints. The highest of all, finish this sentence using the IQ, right? The highest of all y values is what kind of point? Absolute max, thank you. The lowest of all y values is? The lowest of all, absolute min, right? Now, if you have multiple numbers on multiple locations with the highest value, all of them are absolute max. All right? So imagine the sine function. It goes and it hits y equals 1 and falls down, and hits y equals 1 and falls down, and hits y equals 1. Every single peak to the infinity is absolute max, right? But we can cut off 1 period, 2 periods, half a period. Doesn't matter where we cut off for the sine, it's going to still have absolute max. I can cut off sine. You see this? That's 1 period of sine. And if I go carefully over here, and I cut this out, and leave just this part of the sine from pi to, did I lose absolute max? No. I have two absolute max values, right? There's an absolute max at pi comma 0, and another absolute max at 2 pi comma 0. So I went from having one absolute max, right, when I had the full period, I only had one absolute max, which was here. And then I decided to cut this out. As soon as I cut this out, then these two become both absolute max, because this is the whole universe. This is all I have. And the still same absolute min. So we have to be careful with the restricted domains, and we have to compute at the restricted domain. So let's find one wonderful example that we can all enjoy. Problem 35 has a square root. We haven't done anything with square roots, I think. So I'm going to challenge you guys to do the first part, right? Which is the derivative equal to 0 solve equation, right? Get me the insides first. So it's f of x is equal to x squared square root of x plus 1, and then later we are going to deal with this. Closed domain -1 to 1. So we'll just need y values for that. So yeah, that's the easy part. What do you have? Let's see. What kind of derivative is this? Okay, good. I guess I can
Take a walk, come back and 40 minutes.
Oh, this is like a review for your test now. This just, right? Use the product rule to take the derivative, right? That's a test question for you. This is your review now. Good. Go ahead.
Oh, I got him up. Yo, remember what drink did I get you on over there? Ginger ale, right? Yeah, that shit was cooking, right? He was like, hey, another drink. I'm like, what? He's like, oh, he was like, yo, let me run to the bar real quick. Wait, bro, I got where's that? I got
I get the high school.
Yeah, he was DD and I am driver. Or like every time I go out, it's like when waiting for I like nightclub. No, I'm not. Oh, yeah, so you know we should try it. My mom went it's not really surprising to me. It's all little things on the going day-to-day thing. The shower is still
Okay, let's take a look at it together. So what's f prime? It is x squared square root of x plus 1 times times what? I'm using logarithmic differentiation to solve this quickly because I need factor form. 2 over x plus 1/2 1 over x plus 1, of course. Good. Exactly. Quick. Quick and easy. Oh, you didn't practice logarithmic differentiation? Well, that's okay. You did the long way. It's fine. So now, when I have this, I set this equal to 0. I have x squared equal to 0, square root of x plus 1 equal to 0, and 2 over x plus 1/2 1 over x plus 1 equal to 0. The first one has x equal to 0 as a critical number. The second one has x equals -1, right? When you square both sides, you kill the root. And then subtract 1. And now all we need to do is to worry about the other side, but this one is not a problem at all. You move this one to the other side. That's 2x plus 2 in denominator. And then you cross multiply. You get 4x plus 4 is equal to -x. Move x to the other side, becomes 5x. Move 4 to the right. And then divide to get -4/5. So I have 3 critical points which I obtain from this procedure. And as you can see, one of those critical points is actually the end point of the interval. That's nice. So now I need to find all of their y values. So how much is f of 0? Well, f of 0 is 0. How much is f of -1? F of -1 is -1 squared times the square root of -1 plus 1. Well, that's also equal to 0. How much is f of -4/5? Well, we plug that in. We have -4/5 squared times the square root of -4/5 plus 1. This is equal to 16 over 25. And then we have a square root of 1/5. And I also have to compute f of 1. Remember, we're computing endpoints as well. So that's 1 squared, square root of 1 plus 1. That's a square root of 2. And these are all of the points that we have. Now, you can approximate this, using the decimal. 16 divided by 25 times square root of 1/5. So this is what you need to compute is 16 divided by 25 root 5. If you rationalize this, you will get 16 root 5 over 125. Maybe that's easier to compute. I don't know. So what are the 4 points? We have a 0, 0. We have -1, 0. We have -4/5 and whatever decimal you eventually give me. And we have 1 root 2. This is 0 point something. I mean, I don't need to know it at all because I see it's in between. So I know immediately that this is ABS max. because this has the highest y value of all 4 points. Square root of 2 is about 1.4. And these guys over here, ABS min. Absolute minimum. And now this is either a min or a max, but it's relative. It's relative min, relative max, so, right, we were looking for absolute ones. What is this decimal? Did anyone compute? 286, thank you. 286. So we calculated 4 points, and we have 2 absolute min, 1 absolute max. This one is unknown. Could be min, could be max, could be inflection, I don't know. We'll have to learn more, and that's 4.2. So let's restart this and talk about 4.2, which is first and second derivative tests.